Welcome everybody to today's presentation. What we're really discussing today is really ways on trying to get you aware of different aspects and things that you can do to really minimize the downtime, making sure that your analysis keeps on going and that, you know, again, you get more sample throughput, less headaches and things like that. If you're new to GC, and I know lately it seems like we've had a large influx of people kind of migrating over from the LC world, hopefully, again, this will give you some insight on where problems can arise, things to think about if you're developing new methods, just so, again, so that you limit the issues that you may run into as you go on with your analysis. So the primary areas of concern, and of course this is going to encompass basically every aspect of the GC or the system, of course is going to be your sample. The auto injector, you know, we need to get that sample into the system. In doing so, it's going to go into some type of inlet, maybe vaporize, and then pass on to the column, and then lastly get over to the detector and give you some type of signal for what you're looking at. So as we go through this, we're going to kind of go stepwise through that list. So the sample preparation and care, typically, you know, from one lab person to the next, you want to make sure that the sample is being handled the same way, it's being prepared the same way, stored the same way, and there's a lot of things that can actually influence that, and again, either create some issues potentially or help prevent them. You know, sometimes temperature is very important on sample type. Vial seal integrity, this one's actually a really, really large one. There's a whole bunch of different types of vials that we can use, you know, screw tops, crimp tops, snap tops, and those all have a different integrity basically on its sealing capacity, as well as the user who is applying those seals. pH, and this one here, let's just take a moment. That always worries me a little bit when people ask about pH. Because that implies inorganic acids and bases, and those are some of the things that you definitely want to keep out of your GC system. Inorganic acids and bases, as soon as they make it onto the head of the column and they reside there, are going to start chewing away at that stationary phase. So we really typically want to be pH neutral. Now, having said that, we can also use organic acids and organic bases, and those are fine. You know, you also don't have the salts that can precipitate out from trying to neutralize samples and things like that, and those, of course, are not volatile, will sit in your inlet. You know, it may only take a few samples before all of a sudden, you know, your good-looking chromatography starts to tail and doesn't look good, and then you're scratching your head what's going on, and then again, it relates back to the sample itself. Solvent purity is another one. You know, you can get extraneous peaks that may collude, come out as a shoulder, or give you quantitation issues if you don't have really, you know, pure solvents or continuous use of pure solvents. And then, of course, we can also have exposure to light and have some degradation just due to that, in which case, you know, we want to think about using an amber vial instead of a clear vial. So there's a lot just to begin with just the sample preparation and care that's going to help make our analysis a little bit more robust. Then as we get the sample prepared, of course, we need to put it onto our auto sampler, or, you know, if you're doing manual injections, I'll speak briefly on that as well. With your auto injector setup, you know, you could use a 5 microliter or 10 microliter. With our new auto sampler, you can use up to a 500 microliter syringe for large volume injections, and there's a whole bunch of other little caveats to that. You do need to choose solvent washes before and after injection. And this one's actually another kind of key point that does come up quite a bit as well. Depending on the type of application and the type of sample that you have, you may need to really focus on not necessarily only the washes, but the type of solvents that you put into those wash vials. With our auto sampler, you have a wash A and a wash B. Oftentimes, if you have issues with sticky plungers and just really kind of gummy samples that tend to give you issues after a while, choosing a different solvent for wash A, which is typically what the system's going to hit first, versus your sample solvent, which is what you'd really want to use in your wash B, or the last solvent that your syringe is going to hit, is going to be really important in making sure that you rinse out all those residues and, again, make your system a little bit more robust, get rid of that particular issue. With that, typically, the after injection washes are going to be a little bit more important. because after you've done your sample, you know, you've injected it, you've maybe done 1 or 2 washes, and you're waiting for your next analysis to go through, the solvent that's in your syringe is going to start to dry out. And that's going to leave behind the residues in your syringe. So if you haven't gotten rid of those, that can lead into some issues. With the sample pumps, we're really just trying to get rid of any air bubbles, make sure that we've gotten any residual solvent out of there, so we really have a good representation of our sample itself. Plunger speed, typically, you know, you want to get your sample into the inlet as quickly as you can, so that you get, you know, quick vaporization onto the column, nice and quick, nice efficient transfer of the sample. Typically, this is not much of an issue. With our certain applications, again, with our new auto sampler, I believe it goes a little bit faster, so sometimes actually changing this plunger speed and slowing it down slightly is a lot more beneficial and can resolve some issues. Viscosity delays, if you have, again, thick, kind of more viscous type of samples, you'd want to use some type of viscosity delay so that as the plunger's pulled up, it waits for a moment for the sample to actually get up there to the bottom of the plunger so you don't have this air gap in there. And I mentioned I was going to say something about manual injections. If you go through our catalog or, you know, look at anybody's catalog on syringes, you'll see that the needle lengths are different. And that can be really, really key on the type of injection mode that you're doing. If you're doing split injection versus splitless, as well as the type of liner that you're using. Because if you're doing a split injection and your needle is too long and it goes past the glass wool in the middle of the liner, you're not getting the benefit of that glass wool. So sometimes what you can do is, you know, depending on the syringe that you have, you can always stack some inlet septa on the bottom of the base of the plunger so that the needle isn't allowed to go as far as into the inlet. And again, that will make it a little bit more consistent. Or if you're switching between needle lengths, you know, if you have different sized needles and you're just doing some kind of preliminary method development, that could also be an issue that you can run into. So with our typical auto injector setup, you know, most commonly we're using a 10 microliter syringe with the HP point style needle tip. That's the one that kind of comes to the cone and it has a hole right in the middle of the cone. You know, you want to use really good vials so that you don't have any issues with that. Nice caps and septa. Look at the septa material with your solvent as well. There's compatibility issues sometimes with that. Typically, you would want to set up with 3 to 5 sample pumps. And again, the most common would be 3 washes, both pre and post. So if you're using one solvent in A and B, basically this is just going to prevent it from draining vial A. It's going to have you have 6 washes pre and post injection, which is typically enough. But again, those applications where more is needed. So then as we keep going through there, now we've got to look at all the surfaces. You know, now we've got the sample loaded. We've got it on our auto sampler. Now we have all these different surfaces that our sample now is going to come into contact with. Obviously the inlet where it's going to be vaporized with solvents, with the liner, with everything else. It's going to hit the liner. It's going to hit the gold seal potentially right before it hits the end of the column. It can touch the tip of the ferrules, so sometimes the ferrules themselves can be problematic. And then we have, obviously, the GC column typically attached right to the inlet itself, and then, you know, depending on how complex your system is, we may have some capillary flow devices, you know, Dean switches, splitters, and things like that. And then if you're using a mass spec, they also have mass spec components. So we have all this surface area that our sample can interact with. And what we've found is that as technology's increased and the systems themselves have become a lot more sensitive, there's a lot more things that we're starting to see, and that the EPA and these other governing bodies are starting to require you folks to analyze. And so now we have to be a lot more diligent on all the components that we make for the systems to make sure that we make it as easy as possible for you so that, again, you can have a nice, robust, problem-free, hopefully, analysis. And I know that's not necessarily the case. So we've come up with different deactivation technologies now on different types of materials. I think this, we'll keep going. Here we go. So we have ultra-inert liners. We have these flexible metal ferrules that these ones actually don't look like they're deactivated. They kind of have like a purple and blue hue when they are, and they all are are deactivated that way, and these type of ferrules are used with our capillary flow devices, which are also deactivated. We also have now an ultra inert gold seal, because we found that, you know, gold is not necessarily inert, so we have to coat that to make sure, again, that we don't have any degradation issues or adsorption issues with your tricky analytes. We have certain ultra inert GC columns that, again, address some peak shape issues and adsorption issues that we have with some difficult compounds. And then from a detector side, we have now a deactivated FPD, and then our sources. Not only are they inert, but they also can go to higher temperatures, which will help with potentially peak shapes. Again, and a lot of this stuff is just application specific. Not everybody's going to need or benefit from all these different components. So now as we look at the inlet, and what type of things do we have to concern ourselves with? Well, we have obviously the inlet septa, which we're going to pierce with every injection. We have our liner O-rings, our liner, and this is also the type and deactivation of that liner. And I just mentioned the gold seal. We have different types of ferrules that we can use. And then, of course, to make your analysis robust, and again, this goes back to, and I'm going to hit this a lot today, application-specific parameters. You know, your inlet temperature, your flow rates, your split. Not only that, but also your split vent trap. And we'll hit on this again later, because this is still one of the, almost a hidden thing within the inlet that can become problematic over time. A lot of people actually don't even know about the split vent trap. And again, we'll discuss that here momentarily. So the septa type can actually have an effect on your analysis. This isn't as big these days as most companies, if you're not using Agilent septa, most companies have or have deviated away from kind of a lesser quality type of septa. But these really do help. And then again, with that, if you're using a hot inlet, if you have a 400 degrees or even above 350 degree inlet temperature, you know, you'd want to use these what we call bleed and temperature optimized septa. And also if you're using mass spec, these ones don't have the bleed issues that people designate, you know, see siloxane peaks and all of a sudden they think their column's degrading. More often than not, that's either from an inlet septa or typically actually a vial septa. If you're doing the routine, you know, 250 degree inlet, you could use the advanced green septa or the long life septa. And those both work really well. And you'll notice on these septa that there's a little dimple in the middle. It's not a hole that goes through there, because a lot of people, you know, if they have inlet leak issues after trying these, they assume that they're actually getting leaking through that dimple. And that's what it is. It's a dimple. It's basically one little last step to help guide the needle into one point. So if you look at a comparison here of basically a flat septa without the dimple versus our center guide septa, you can see after even 100 injections, you basically have blown a hole into that septa. And of course, that is going to give you potential leak issues and things like that. If you get any oxygen into your column, you're going to oxidize the column, have high bleed, and just your problems are going to compound from there. So again, you want to start with a good septa, change it often. You know, the typical cost of a premium septa is about $1.50 as opposed to your column. And again, it only takes a little bit of a leak to destroy a column. So just be proactive, change it frequently, and make sure that you're using a good septa. And you know, you could also get the coring, and that could get in your inlet, help with degradation of sample and things like that. So there's a whole bunch of other issues that can combine from just even from the inlet septa itself. So then past the septa, now we have the liner. And the liner is really, really important, especially if you're using a splitless injection or an MMI. These two are going to use the same type of liners and have the same functionality. You also have a PTV inlet, which uses a liner. And then here I didn't highlight the on-column or the purge pack. The purge pack uses a sleeve, but you get one type, and that's it, which is still important. And then, of course, on-column, your syringe needle is going inside the GC column. So you really don't have the issues from a liner aspect on that, but there are still other aspects of the on-column inlet that we need to be aware of. And with this, I'm going to talk about really kind of focus on the splitless inlet, and again, the multi-mode does the same thing basically as the split splitless and the programmed temperature vaporization PTV inlet combined. So the three key variables of a liner are going to be the volume, and that one's actually going to be a really important one, as we'll see here shortly. The treatments or deactivation, another very key aspect, as we hit on earlier with the ultra inert liners and the sensitivity of systems, that can become very, very important. And then, of course, there's a whole bunch of different designs of liners that have different characteristics. You know, either some glass wool in it, placed high, placed low, you know, cups, inverted cups, tapers, frits. There's a whole bunch of different characteristics or designs that we have for liners, and they all play an important role in getting your sample vaporized. So what the inlet liner is supposed to do is provide an inert space for the liquid samples to be uniformly vaporized and moved onto the column. And there's a lot of things that play into this as well, depending on your parameters, you know, inlet temperature, even the type of carrier gas, because that will actually relate back to inlet pressure, which is going to be key, as well as the solvent. And we have a table down here. And what this is showing you is that with a 1 microliter injection, which is a very, very typical sample size, with varying different solvent types, we have a different vapor volume that is created within the inlet. And you can see that maybe, you know, this hopefully is raising some flags with you, because this might be problematic, because there is going to be a certain volume that our inlet, and especially our inlet liner, can accommodate. And we're going to key on here water in particular as we go through the next few slides. So with that, we want to choose a liner with the right volume to accommodate the vaporized sample. We want to make sure that we have glass wool. If we're doing, you know, split injections, we want that placed in the middle. If we're worried about backflush, and we're going to really get into that here in the next couple of slides, we want to maybe look at a different type of liner that helps restrict that and focus that sample onto the head of the column. And then hopefully remembering from that table, with different liners, we either have like a 2 millimeter ID liner, which you can see holds only about 240 microliters of vapor volume, and then our standard ones, which is a 4 millimeter ID liner, holds about 972. Going back to that previous slide, you see that water has a vapor volume under these conditions even of over 1,000 microliters. So it already exceeds the vapor volume or capacity of a 4 millimeter ID liner. So with that, we actually have recommendations for most samples, and there's different ways and things that we can manipulate with that to change that. But recommended volumes are 1 or 2 microliters for organic solvents. And really, if you're doing water, try as best you can to limit it to half a microliter of water. Water is the most problematic solvent to be used just because of its expansion coefficient. A lot of people think, you know, the column is going to degrade or things like that. The column's not really the issue at all. It's all the inlet. So with that, we can determine if you're going to have an issue right from the get-go or not by using a calculator. So we have this pressure flow vapor volume calculator that you can download from our website, and maybe you've had this in the past. This is actually a newer version that came out within the last, I think, month or so. It looks a little bit different than maybe what you'd seen in the past. This is now what it looks like. You end up with 3 different icons. If you choose all 3 calculators on your desktop, you have the vapor volume, and then you have the pressure flow calculator, and then a solvent vent calculator if you're doing large volume injections with a MMI inlet or something like that. So how it works is you choose your solvent type. In this case, we're choosing hexane. You choose your liner type, and this one is the standard, say, split injection liner with the glass wool in the middle. We're going to do a 1 microliter injection. We're using a pretty standard inlet temperature of 250 degrees, and our column head pressure is only going to be 10 psi. And when we put all that in, we can see that the estimated volume is 195 microliters, and we're only at 22% capacity of that liner. And we're still in the green, so it says, oh, go ahead. You're not going to have any backflash issues. You should be able to transfer that sample reproducibly onto the column injection after the injection. Now, if we use those same parameters, 10 psi, 250 degree inlet, 1 microliter injection, same liner type, and we change to water, now you can see that we're going to have problems. We're at 166% capacity of our liner, and what that means is that when your sample is vaporized, it creates that pressure cloud. It's going back out your split vent line. It's going back into your carrier gas supply line that feeds your inlet. It's going all over the place. And this would be when you inject a blank or you just hit start on your GC and all of a sudden you see a portion of your sample. This would be one of the main causes of that, is because you have parts of your sample, your analytes, kind of pigeonholed in all these slightly cooler areas right outside the hot part of the inlet. When you inject a solvent again, it's going to expand back into those areas. It's going to cool the inlet just ever so slightly, so it almost creates a vacuum, pulls those things back in, and then you chromatograph your sample when you haven't even injected it. But, and this is the nice thing about this calculator, we can go back and say, okay, well, what happens if we're only going to do a half microliter injection? Then we're within the capacity of that liner. We're not going to have any backflush issues, and we should be able to, again, have a reproducible injection and less problematic analysis. If by chance we really do need a 1 microliter injection because we have very low concentrations of something in there that we want to analyze, what we can do is actually increase our inlet pressure. So your newer GCs with electronic pressure control have the ability to do pulsed injections. So at the time of injection, what we can do is if our analysis is taking 10 psi to move the carrier gas through the column at the rate that you want, we can actually increase the inlet pressure only for the time of injection, inject the sample, blanket the expansion of our solvent, get that passed onto the head of the column, and as soon as it's there, basically shut this pressure down back to 10 psi and run our analysis. So there are tricks that we can use to combat that, but we definitely want to use a tool like this pressure flow calculator to make sure that we are not going to have any issues from the get-go. So then the liner treatments and deactivations that we have for that, again, we want to make it nice and inert so that we can prevent the active components from absorbing or degrading on that glass liner or glass wool surface. That'll lead to tailing, loss of response, Endrin and DDT for those folks out there that are doing some environmental analysis. Those will degrade in an inlet and you'll get degradation products. And so even at that, there's some different ways that we can look at issues from peak shapes and let you even know if it's coming from a liner or if it is a column issue or something like that. So we want to make sure that we have a deactivated type of liners. And I'm not going to go through all this. This is for your guys' reference. I believe you'll have a copy of this after the presentation, so if you wanted, you could go back through and look. But as you can see, we have so many different types of liners that are all going to be beneficial for different types of applications. And so choosing the correct liner is going to be key, and again, minimizing issues that you may have. Continuing kind of with the injection modes of the splitless inlet, and I mentioned that we were going to kind of key in on that. The split injection is the most common injection technique. The nice thing about that, not only does it reduce the amount of sample that you're getting on the column, it reduces all the garbage. It's pushing that out the split vent. It's also the most efficient injection technique. If your flow rate is 1 mil a minute and you have a 20-to-1 split flow, you have 20 mils a minute of split gas going out the split vent. So you essentially have 21 mils a minute going through, passing through your inlet at the time of injection. So what that does is that really, as soon as that sample is vaporized, it pushes that sample onto the column much, much more quickly. And so you end up with tighter sample bands, sharper peaks. So when developing a method, even if you're not going to be able to use split injection, I personally would recommend starting off in split injection. You're going to get the best chromatography, best resolution. Then we can always peel that back, go back into splitless mode, and try to mimic those parameters, again, maybe with a pulsed injection and things like that, to get the chromatography that you need. With that, because you are splitting the sample, it is primarily used for high concentration samples, obviously. And with that, there's something key with the inlet liner. So it must be inserted so that it actually floats off the bottom of the liner, or excuse me, off the gold seal. So with that, they are, I believe it's on this next slide, with our standard, and this is like the most commonly used split liner, there's a little nub on the bottom of the liner, and that's there to help keep it off the gold seal and help facilitate that split flow through the inlet liner, up and around and back out the split vent. So that's one of the key aspects of a split liner is that nub, as well as actually the glass wool. Because when you inject into it, since your flow rate through there is a lot more quick, you want to have something that's going to help provide a little bit more thermal mass, to help a little bit more mixing to make sure that you get a good representation of the high boilers and the low boilers in your sample. You don't want any inlet discrimination right from the get-go. And sometimes you'll see frits over here and certain other things that are placed right about the middle of the liner, and that's basically to help, again, facilitate getting a good representation of your sample onto the head of the column. Conversely to split injections, splitless is for trace level analysis. So when you have those really, really low concentrations, you know, part per billion or even lower in some cases, type of concentrations that you're looking at doing. Basically what the splitless injection is a paused split injection. So you're basically shutting that split vent off at the time of injection. So all the flow is going onto the head of the column, and then at some time after the sample's moved mostly through the inlet, if not all through the inlet, then you open that split vent up again and hopefully evacuate any residual solvent without affecting any of your analytes. And again, with that, you know, the timing of your split vent, your purge time, your split flow basically coming back on, it can be really, really key in making sure that you're doing that right, that you're not having any issues. You know, split vent flows become important at that point, depending on the type of residues that are in there. You want to make sure that you're really pushing them out the split vent, giving it enough time to evacuate the inlet before your next injection. One of the benefits sometimes with a splitless injection is that you don't necessarily need to run it as hot. So if you have some thermally labile compounds, things that are going to degrade at 250 degrees, but you have other components that won't vaporize or volatilize at lower than 250 degrees, the splitless injection actually allows you to go down to 220 or maybe even 200, just because the sample itself is going to have a lot more residence time in that hot heated zone. So it will make its way through and onto the head of the column. Just like split injection liners, we have different designs for splitless. Again, you'll see glass wool here at the bottom. This will help with the heavier high boiling compounds, volatilize again right before they get onto the head of the column. One of the key things with splitless liners is the outer diameter is actually a little bit larger than for split liners, because again, remember in split, we want to help facilitate that split flow going around the split liner and back out the split vent. And with the splitless injection, we really want to focus the whole sample onto the head of the column, so we want to occupy the whole volume of the inlet itself. Liner maintenance. These are one of the things on here. Obviously, you can see that this is a grossly contaminated liner. These are oil samples that were injected. You can visually see the residues that are in there, and obviously you're going to have some problems, more so probably with this one. As you can see, this little taper here where the column is inserted is completely blackened as well, so you're getting all those residues not only in the liner, but also in the head of the column. Whereas here with this type of liner, the glass wool is there to help trap some of that. It's not going to trap it all, but it's going to do a lot better job than in this case, this liner. And it's not this liner that's the problem. Remember earlier I mentioned the length of needles when you're doing manual injections? So my colleague that did this actually did it manually, and he used a needle that actually went past the glass wool and injected below it. So he got no benefit whatsoever of the glass wool, injected the sample here, and you can see that it kind of spilled down all the way into the column with more and more injections. So this is one of those key things, again, that you're going to, and it's going to be application specific, how frequently that you're going to want to change whatever style of liner that you're using. With that, you do definitely want to keep the same type of liner as well, because glass wool here and the amount of glass wool and glass wool up here, and again, I mentioned the ODs of the liners, that's all going to change the flow through the inlet, and that can have an effect from, if you're routinely doing analysis with, say, this type of liner, all of a sudden you run out, you need to change it, you put in this type of liner, glass wool is at a different spot, liner volume is a little bit different, or the OD is a little different. The way your sample is moving through that inlet is going to change. So you aren't going to see the same thing. So you want to make sure that you replace, have some liners on hand, replace it when you need to with the same type of liner. With that, of course, liners can be expensive. A lot of people will talk to us about deactivating them themselves. Really the only advantage of that is obviously a reduced cost. You have a series of liners that you put money out for, but now you're going through the whole procedure of cleaning it. The bad thing with that, it's time consuming. If you have glass wool in there or cups or, some of the frits and things like that, it's going to make it a little bit more difficult to clean these type of liners. With that, reproducibility of the liner is compromised. If you're using more than one lab tech, unless you have very detailed people with very detailed instructions, you may have variability from liner to liner. Mostly, I would say that the deactivation process is probably going to be the most forgiving, potentially. It's if you're inserting any glass wool into the liner. Because the density of that, the amount of that, the placement of that is going to be very, very important and have a big influence on your liner. Just like I said, switching between two different types of liners, just having a different amount of glass wool in the same type of liner can actually change the resistance of that liner, change the flow dynamics of the inlet, as well as the way that the sample is getting onto the column. One of the difficult things with, if you do start to have issues, many of the chromatographic problems that actually arise from the inlet are blamed on the column. The column is actually, the poor little guy, he's blamed for just about every issue that there is within a system. But with that, it is more often than not, it's actually a dirty liner that is going to contribute poor peak shape, irregular baselines, because you may have residues that are kind of coming off continuously. They're going to go through the column, get to the detector, give you wavy baselines, a whole bunch of other weird things. You can have an effect on resolution as well as response if you have, things that these analytes of interest are going to react with or interact with upon injection, then they're going to start getting to the column bad to begin with. Again, with that, a lot of the dirt that's in the liner is also getting on the head of the column. So you want to make sure that when you change a liner, typically you're going to trim the front end of the column. And don't only trim it, 2 inches, trim it a foot, 2 feet, depending on your analysis, maybe even longer. The deactivation and making sure that you're changing liners frequently enough anyway is going to be really especially important if you're looking at phenols, organic acids, pesticides, all these type of compounds that really have these active functional groups on there that can interact with different residues and just junk in your inlet and create issues with that. And as you see here, we got phenols here with EPA 8270 compounds. With our UI liners, we actually kind of key in on this, and we actually have a test that we do for response of 2,4-dinitrophenol, in part because that's one of the more active problematic analytes for liners, but also to address that for the people doing some of these environmental analysis such as the 8270. And that's only one of the issues associated with the liner and this type of analysis. There's other degradation issues as well that can come about from residues building up in liners or just poorly deactivated liners. So to conclude on the liners, and we spent a bit of time on that one, it's the type of inlet in your GC obviously is going to have a huge impact on that. the manufacturer of your GC and everything else. Concentration and type of sample. If you're running high concentrations, you want to use split. Trace analysis, you're going to want to be doing splitless or PTV, and again, that includes the MMI. Flexibility, broad range, you can use both. For heat-sensitive compounds, if you really do have these tricky compounds that are just hard enough to get through the inlet, let alone the column or anything else, you may want to consider on-column injection or PTV injections where you can, inject it at 40 or 50 degrees and raise the temperature ever so slightly and gently so that you can get those compounds to move through the inlet before they start degrading. After that, sample size, your solvent type, and injection volume. We want to make sure, obviously, that we have very, very clean samples. We want to limit those residues. We're going to have residues in everything that gets injected. Standards have residues. So, keep that in mind as well. If you're doing a lot of method development, all you've done is inject, 100 or 200 standards to dial everything in. All of a sudden, you follow up with one sample. Sample is going to be slightly different, but maybe there's a buildup of those residues that are also going to affect that. Choose the special features, the characteristics that'll help with your analysis type, your sample type. And then with that, touch on it a little bit briefly, optimize the chromatographic condition. So not only, again, your oven program column and things like that, but we want to make sure that we're getting the sample there efficiently first to begin with. And again, if you're doing method development, I would highly recommend starting with a higher concentration sample, running in split injection, work that way, and then go backwards if you need to. So now we're going to get into some non-optimized operations, some other things that can give you some headaches and make your analysis not so robust. And there's a lot of things that can play into this, and this comes actually a lot. People taking out a liner and looking at the liner, not seeing anything, thinking the liner's okay and putting it back in, having these issues that we just mentioned, and then blaming their column. Part of the issue is you're not seeing, hopefully you're not seeing residues in your liner, but that doesn't mean that they're not there. If you can see them, that's an extreme case. And I would say that more than likely you've let the issue go a little bit too far before addressing it, and so now we got to dig into the system a little bit more. Get in there, change the gold seals and things like that, whereas maybe we could have just replaced the liner a little bit more frequently. If you do take out the liner and reinstall it because it looks clean, these are pliable O-rings that are on there. They may not seal as well with the second time. They're also in under heat for a certain duration, a week or month at a time, so that may disform them a little bit. The gold seal themselves, this is another thing that people take out and inspect, and if they don't see it, if they see it nice and shiny like this, they'll reinstall it. Or if you don't look at them, I've had many customers that have actually taken them out and go, holy moly, look at all the stuff that's on the bottom of even the gold seal. With that, this is also a good picture not only for them residues, but see this nice shiny line in there? That's a groove that's created when you actually seal that reducing nut to the bottom of the inlet, which seals the inlet. So if you reuse these, and there's a little bit of wiggle room in that reducing nut, as you press that against the bottom of the inlet, if that seal doesn't line up perfectly, then you have a little channel where you can have a leak. So I would recommend, if you're, keep some gold seals on hand if you're reusing them. Just keep in mind that if you put everything back together and you have some leaks or something like that, this could definitely be the issue that you're having. You don't necessarily want to just come in here, clean off the gunk, and put it back in and go about your business. Sometimes you can get lucky with that, but again, this would be one of those aspects where you spend all that time doing it, turn everything on, and then you have to just go back in and break up the system apart and replace that as well. Again, anyway. Did mention earlier on the split vent trap. This is actually kind of the picture of the trap. This is the trap holder. This sits behind the inlet, so your inlets would be down here. And so it's in this little cubby hole underneath that back long plastic cover that goes over the whole back of the GC. I've spoken to more people than not that haven't even, well, one that haven't even known that they have this, but know that it also hasn't been changed in 5 years. So this is something that you definitely, again, also want to be proactive on. Probably replace it every 12 to 18 months. Again, this will be a little bit dependent upon your application. High split applications, you're going to have more stuff going through this trap than, you know, splitless and things like that. But again, just be proactive so that you don't run into those issues. Because when this gets clogged, it can actually affect the flow through the inlet, affects the flow rate through the column, and you have things shifting around. You may have, you know, peaks that just start popping up, and it could be because, again, if this isn't working efficiently, the stuff that's supposed to be going out through this little copper line is building up, and it's building up closer and closer to the inlet, and which makes it a lot easier to get it back into the inlet and chromatograph it. Good column installation is also very key. What we want to do when we install a new column, install it. Obviously, we want to make sure that we don't have any leaks that we notice. We want to do an installation check, and there's a few things we can do with that. Obviously, once it's installed, it's leak-free. We want to condition the column, and then we want to obviously set our linear velocity or our flow rate, do a bleed profile so that you know what the column looked like when it was installed after conditioning, and then run some type of test mix. And by test mix, I actually mean standard. A lot of people want to, you know, get the column test mix, run those, make sure the column's good. Really the best way to do that is to run your standard, because it's going to be more specific to your system, your carrier gas type, your oven program, your detector type. It's going to be a lot more telling of any potential issues than running our column standard for your particular application. With that, we have two different types of ferrules. We have 100% graphite, and we have the graphite Vespel ferrules. 100% graphite are more forgiving. They're softer. So if you're new to GC, sometimes I would recommend 100% graphite ferrules. They also don't necessarily swell and shrink upon heating. With graphite Vespel ferrules, these are a little bit less problematic. They can't flake into the column and things like that when you install it. You wouldn't want to use graphite ferrules on a mass spec, obviously, and certain other detectors that if you do get flakes in there, you can't take the detector apart to get them out. So oftentimes graphite Vespel ferrules are recommended. We have newer column nuts, which also make it a little bit easier to tighten the columns in there. You don't need a wrench any longer. This is the inlet and most detector type of column nut. This is the mass spec one. It actually uses the same size ferrule as the inlet, so this helps kind of limit or minimize the amount of ferrule packets that you have laying in your drawers. You want to make sure you have the right distance. This is kind of the old school way to use whiteout at the bottom of the column. The easiest way, and I recommend this for everybody, is to use an inlet septum, because it also will hold your column nut in place when you go to install it. So you'd want to put your septum on, your column nut on, your ferrule, slide them all back, trim the column in case you've gotten any ferrule particles in there, and then slide this all the way back up so that you have your, in the case of the splitless, 4 to 6 millimeters of the column sticking above the tip of the ferrule, and then install it, and then you should be good to go. When you cut the column, it should be really, really easy to do. The easiest thing to do or use for that is the ceramic wafer. It's the least expensive one as well. Just really quick and easy, drag it across, and the column basically falls apart. We also have the fancier carbon-tipped pencil or sapphire cleaving tool. Definitely do not use scissors or a file or a razor or anything like that. That's going to give a really poor cut to your column, and it could look like this. And as you can imagine, as your sample's trying to get in here, if it's interacting with all of this fringe, you're going to start off with bad chromatography. So just make sure that you start off with a nice, good, clean cut. You want it nice and perpendicular. If it's at an angle, as you can see with this one, parts of your sample are going to have an easier time getting into the column here than they will here. So you may have tailing of your compounds. You may, depending on how far you've installed it even, you can get peak splitting, and it's all from a column cut and installation. So again, there's a lot of things that we can do initially that, again, people blame on the column, but again, it's really inlet related and how the column's installed as well as not just the liner. How tight is tight? Typically you want to tighten it up, whether it's the self-tightening column nut that I just showed you or the standard column nut, until the column is snug in there, so you can pull on the column. As soon as you feel it get a little snug, turn it a corner turn, and it should be set. If you over-tighten it, and again, this is going to be a little bit easier to do with the graphite vesicle ferrules, you can crush the column, you can have inlet leaks, you cannot see your peaks because you can, essentially collapse the whole column or get the ferrule in there. So again, these are just some of the issues that you can run into just from a column installation. To do a leak check on that, I highlight this, do not use Snoop. Snoop is a soap solution. If you get soap into your column, it's really hard to get soap out of your column. Those components in there are really, a lot of them are not that volatile. Depending on your type of column, it could be a really big problem. Instead, use an electronic leak detector. If your connections are cold, you can use a 50-50 mix of IPA and water, and you can use this basically on anything. It'll bubble up basically almost like the Snoop would. And then another thing to do, and we recommend this oftentimes for multiple reasons, is to inject an unretained compound. And what an unretained compound is something that's not retained by your column. It's going to move through there. Oh, I thought we had one right there. Move through your column over to your detector as fast as the carrier gas goes. So the nice things about this is that it's going to let you know if you have any issues at all. If you set your flow rate to 1 mil a minute, your hold-up time, which is also in your parameters of your inlet section or your column section, if it says 1.34 minutes, you should roughly see your unretained peak or compound come through at roughly that time. I will tell you right now that 99% of the time it will not come out exactly on that. From column to column, it will not come out exactly the same time. There's dimensional tolerances in the column that change the restriction, which ends up changing the velocity or the flow rate just ever so slightly. So you can have things bounce around a little bit that way. So that's another reason why we typically recommend injecting a non-retained compound and actually measuring either your flow rate or your velocity. So for an FID detector, methane or butane from a disposable lighter, just a little bit of the gas in there, works very well. For an ECD, we need to have something that's halogenated to get a good signal. You don't want to inject any liquid. That will, kill your detector momentarily. So you just want a little bit. You just want to see a peak. So you just want the headspace of that. Again, specific detectors are going to require something specific that they're going to react to. Again, these are the most commonly used things, and it really also is going to depend upon your column type as well. With a TCD, we can inject air, and we can do that with a mass spec as well, or butane. And you should get a nice, sharp, symmetrical peak from that. Again, it's not interacting with the stationary phase. It's giving you a picture of the flow path, your column installation, any leaks or things like that that you have within the inlet itself upon installation. And if it does start to tail or anything like that, if this is tailing, this means that your carrier gas is essentially, in a way, tailing. That means also that everything else coming onto your column is going to be tailing. So you want to make sure this is just a quick, easy check. Again, with a 30-meter column, it's about a minute and a half, 1.3 minutes or so. So it's a really quick verification that you have a good installation, that you're not going to have any issues. And it's a lot easier to do that before you go ahead and condition the column. Go back and then afterwards think everything's honky-dory, inject your standards, and all of a sudden you've got chromatographic issues. So just take that extra minute or two, if you can, to inject an unretained peak and get a good picture of your system. And here I'm just going to skip through this. This is just how to calculate your linear velocity. And the same with if you wanted to calculate the volumetric flow rate, because a lot of methods out there are designated as 3 mils a minute. This is one of them. Again, measuring it is going to be a lot more accurate than relying on the system or even a flow meter to make sure that your system is giving you the right flow. Column conditioning, again, once it's installed, we've ensured that we don't have any leaks. It has to be leak-free before conditioning. what you want to do is heat the column to the lower of the isothermal temperature. So there's two temperatures on a column, the isothermal or the program temperature. Or if you're only taking a column up to 150, you want to condition it maybe at 170 or 180. You want to do that for 1 to 2 hours. 2 hours is typically the most consistent time. Really don't need any more time than that. And you don't have to program it there. I know I run into a lot of people that'll program at 5 degrees a minute to get up to the isothermal limit, leave it there for two hours. Some people do it overnight, which can not be good, especially if you have a leak. But 2 hours should be sufficient. You don't have to temperature program it. I just walk up to the GC, key in the temperature, hit enter, let it do its thing, come back in 2 hours, and I'm good to go. With that, if you're using graphite vesicle ferrules, what I would do, get all your temperature zones up, even ramp your oven temperature up initially to 325 or whatever it may be, drop it back down again, and then snug your column nuts, and then go ahead and condition the column. You want to make sure, because the graphite vesicle ferrules can swell and shrink and cause a little bit of a leak initially, so you want to make sure that you do that. With those self-tightening nuts, they apply pressure on there all the time, so that should not be an issue. So when we're conditioning and we're going to be using our column, what does normal column bleed look like? It's generated by the elution, continual elution of normal degradation products of the column stationary phase. So this is what your typical column bleed will look like. It'll be a little higher for more polar compound or columns, lower for less polar columns. Also relates to stationary phase film thickness. But as you program it, when it gets to about 20 to 30 degrees below the upper temperature limit of the column, that's when you should start to see the baseline rise. Once it gets up to the top temperature, it should be flat. If it's continuously going up, then I would shut the system down, make sure you don't have any leaks, because that's a bad sign. That could be oxidation of the stationary phase, chemical degradation of the stationary phase. So you could have other issues that way. Again, it's elevated baseline at the high temperature. It's not a baseline, high baseline at low temperatures. That's a sign, again, of some type of oxidative damage or chemical damage. It's not a drifting baseline. And this is a key one. You cannot chromatograph your column. The only way you can do that is if you put the end of the column into a vial of solvent, raise your temperature up to drive off the degradation products, and then take that vial and re-inject it into your column. That's the only way you can get column bleed peaks. So if you're running your analysis, and here's your analysis of these nice looking peaks here, and as it goes up, you see the baseline actually goes up and comes down again. This is all contamination. You got something big here because it's going up and coming back down. Again, it should go up and flatline. So this is all contamination, more than likely coming from your inlet. So as we see here, same column after inlet and column maintenance. The run was shut a lot shorter than the 70 minutes on the previous one. But here you can even see at about the 36-minute mark, all this stuff right here on this is now gone. So we've trimmed the front end of the column. We've done the inlet maintenance, replaced the liner. We may have, replaced the split vent trap and things like that, gotten rid of that contamination, and we're good to go. There's been a lot of advances in columns. We worked on the bleed, and a lot of this is driven, again, by the sensitivity of the systems themselves and the new applications that are coming out because of what we can see now that we couldn't see before. So there's a lot of work done in columns as well. With column contamination, it mimics nearly every chromatographic problem, same as the inlet issues. So this is where it gets a little bit tricky to kind of discern if it's an inlet problem or a column problem. But typically, you can almost go by peak shape, actually, to pinpoint at least, or put some focus one area versus the other as far as chromatographic problems or peaks go. Some of the symptoms that you'll see, again, like we did with liners, poor peak shape, loss of resolution, change in retention, baseline disturbances. Again, this could be just buildup of material on the column that starts waving through there. And I apologize, I'm speeding up because I see we're running out of time here, or just about out of time. Typical samples that contain a large amount of residues, if these are things that you're looking at doing, biological samples, I would say, are probably the most problematic. But again, all these samples have a lot more residues than some of the others. That these can be, these are where you want to be a little bit more proactive on changing liners, and doing inlet maintenance a little bit more frequently, as well as trimming the column. Septum and ferrule particles, you can get, if you have a mass spec, if you're seeing siloxane peaks, this is typically coming from either inlet septa or more commonly vial septa. We didn't speak about gas traps today, but you can actually get impurities coming over from gas traps if they've been used up and you have a dirty tank of gas or what have you. So again, the one fun thing, so to speak, of gas chromatography is that there's so many things that can go wrong or that can create issues, and finding them can be really a trick. So again, being proactive about a lot of these things will at least ensure that you spend your time focusing in the right area, hopefully, if one of these issues do come about. Non-volatile residues, they come out of your column. They may come out on the second run as a carryover or something like that. Or excuse me, the semi-volatile ones. Non-volatile, those are going to be the ones that are going to be more problematic. Typically react with your analytes as they're loaded onto the head of the column. So if we have those type of things, again, sample cleanup, spending a few more minutes per sample could potentially, save you time down the road with maintenance and things like that. Packed injection port liners, glass wool, or there's some with actual packed material in there that can potentially help. Or we can also use guard columns. If we have known residues, we can put a guard column on the front end of our column that this becomes now a sacrificial piece of column. We have some type of union here, obviously, but this protects our more expensive analytical column. With that, we have different types of connectors. We have these glass press fit connectors or splitters if we're doing a two-column analysis. These work, but they're not nearly as robust as some of these more recent mechanical style, low dead volume style connections that we have. This is a splitter, and this is what we call our ultimate union, and they all use these funky looking Christmas tree-like multi-metal ferrules. Again, with a purple hue, deactivated, everything's deactivated. So again, we're making sure that we have a nice inert system. If you do have some non-volatile contamination, one key thing, do not bake out the column. You can actually polymerize that material onto the column. Maybe do your front end maintenance and cut off about a half to 1 meter of the front end of the column, which is 1 to 2 loops of the column. 2 loops is a meter roughly. You want to go in and change your liner. You may actually want to get a cotton swab and with some solvents and rub the inside of your liner. Don't use a gun barrel brush, especially if you have the deactivated inlet weldment. You'll take that deactivation layer right off and create more issues. You can turn the column around. The side that's sticking in the detector really doesn't see the sample at all, so it's a very, very clean part of your sample. So if you're in a pinch, you need more lifespan out of that column, turn it around. You also put that non-volatile residue closest to the detector, so hopefully it'll work its way back out. With biological samples, I've seen more than one time where customers actually had to cut the column in half to regain chromatography. And don't be so concerned about this half meter to 1 meter thing either. Even when you cut the column in half, as long as you adjust for it, you're not going to lose half your resolution. It's a big misnomer out there. I'll skip through this. You guys can read about that. It's looking at the test probes and the way that the samples have been, the columns have been tested. If you're going back and forth through vendors, not happy with one thing, again, you think it's the column, definitely try another vendor, but we all make columns a little bit differently as well. So make sure that you're aware of that. Again, just bleed and temperature. We don't want to, look at a DV5 from us that was run isothermal versus a same 5 type of phase from another company that, ran it at a temperature program, and you look at it and go, oh, we got so many more plates on that one. That's, that could be a little bit misleading. The way that the column is tested actually determines some of those values. So you want to, compare apples to apples, make sure that if the columns are tested the same way. Detectors just here briefly. Temperatures, you want to make sure typically your detector temperature is higher than your oven temperature so you don't recondense anything on there. You want to make sure that you have the appropriate flows So with an FID, your flame stays nice and robust, stays lit. And then with most detectors, your general preventative maintenance, cleaning sources, replacing jets. Detectors are typically the pretty easiest piece of the system to maintain. There's not much that has to be done there because whatever can get through the system and create issues does, and everything else is trapped most oftenly in the inlet or the column itself. So I know, again, kind of whizzed through here the last few slides. In conclusion, maximize consistency of the sample stability and handling. That's going to be key just to make sure that your analysis is robust from the get-go. You want to make sure that we're using correct inlet and auto-injector parts and conditions. Try not to reuse O-rings and ferrules and things like that in the gold seal. Change your liners. Make sure you're using a good column. Trim the front end of the column consistently. Make sure that again, any residues that are building up there, and they are building up there, you want to make sure that you remove. When changing a column, again, I mentioned this briefly, one column to the next, make sure that you measure the linear velocity. This is going to make sure that your analytes and resolution maintains itself from one column to the next. You can get things to pop out exactly where they were with the same resolution if you measure the linear velocity much more so than you can if you just rely on the system to be accurate. You want to make sure that you're doing a regular routine of inlet. This is application specific. Again, if you've injected 100 samples and you start to see tailing, go in, replace the liner, trim the column, keep a logbook. Make sure that every 100 samples or have a slight variance in that, go in and do the same thing again, just to help prevent yourself from having any issues down the road and having to tear in the system. And we did go a few minutes over, and I apologize. With that, we are finished with the presentation. If you have any questions, you can certainly call in. This is the shortcut to get over to myself as well as my group. You can send emails in here. There's a group of us that monitor those as well. We still have a fax number up here. It comes in electronically for anybody that does have issues with sending files and things like that because of limitations within your own company. And again, I apologize for going over a little bit, but thank you everybody for attending today.